So for the next subunit of this topic, we're going to look at the types of different organic reactions, in particular nucleophilic substitution reactions, electrophilic addition reactions, electrophilic substitution reactions, and then reduction reactions. So the substitution reactions of saturated alkanes, which we looked at previously, involve homolytic fission, creating free radicals that possess unpaired electrons. Remembering that the formation of chloroethane happens between ethane and chlorine, using UV light as the initiator. So the chloroalkane is produced at very different properties from those of the alkane, which can undergo further substitution reactions, producing a wide range of compounds with different functional groups. The reason for this is increased reactivity is the highly electronegative chlorine atom and the polar halogen carbon bond. Therefore, the partial positive charge makes the carbon atom electron deficient and therefore susceptible to attack by nucleophiles, electron-rich species, which are capable of donating a pair of electrons to form covalent bonds, which we looked at earlier. Now, there's two types of nucleophilic substitution, which is known as the SN reactions. We have basically either SN1 or SN2, and it depends on whether the halogen alkane is a primary, secondary, or tertiary halogenoalkane. So that's what we're looking at now, SN1 and SN2 reactions as they pertain to nucleophilic substitution. So as we look at SN1 and SN2 reactions and which of the halogenoalkanes undergo which mechanism, we have to break down the different factors affecting the rate of nucleophilic substitution. Okay, and one of those factors is the solvents. So solvents can be broken down into two different types, okay, polar, which have dipole moments due to different electronegativities, and non-polar, which all have similar electronegativities in their atoms. They can also be divided into protic, which are polar solvents with OH or NH bonds. This allows, of course, hydrogen bonding. Okay, so examples of protic solvents are water and ethanol. And then we have aprotic, a polar or non-polar solvent that doesn't have OH or NH bonds, and also doesn't have any source to provide protons. So examples of those are acetone, which is polar but aprotic, ethane nitrile, which is polar but aprotic, or the two non-polar aprotic solvents, benzene and hexane. So in summary, there are three main types of solvents: non-polar, polar protic, polar aprotic, and there is no such thing as a non-polar protic solvent. So nucleophilic substitution in primary halogenoalkanes proceeds in one step. The rate determining step, or the slow step, involves both the halogenoalkane and the nucleophile, so the rate of reaction is dependent on both concentration of the reactants. So therefore it's a second order reaction, okay, second order. And therefore it's bimolecular because it requires two molecules, both the halogenoalkane and the nucleophile. Okay. As there are two reactant molecular entities involved in this chemical event, the molecularity is determined as being bimolecular. Okay, that's why it's known as a bimolecular reaction. But remember that molecularity is not the same as the order of the reaction. Okay. Now, in terms of solvents, polar aprotic solvents are preferred, which are those, of course, unable to form hydrogen bonds. Okay, so if you're going to have an SN2 reaction mechanism happening, the reactions usually occur in polar aprotic solvents. Okay, solvents that don't have hydrogen bonds, like propanone and ethanoate. If there was some form of hydrogen bonding, the solvent would bind to the nucleophile and therefore inhibit its action in attacking the transition state. Okay? So this is an example of the SN2 reaction mechanism which you have to know. Okay? So this is the reaction between chloroethane and aqueous hydroxide ions, and it yields ethanol and the leaving group, the chloride ion. The hydroxide nucleophile attacks the partially positively charged carbon atom, forming something known as a transition state that involves both the halogenyl alkane and the nucleophile. This has a partially formed covalent bond between the nucleophile and the carbon atom, and also a weakened carbon-bromine bond that has not been completely broken. And you see that as the dashed line in the unstable transition state. In this backside attack, the nucleophile attacks the electrophilic center at 180 degrees to the position of the the chlorine leaving group. The large halogen atom creates something known as steric hindrance. So this basically says that the hindrance is due to the large size of the constituent, okay, the large halogen, and this prevents formal attack by the nucleophile. As the reaction proceeds, the entering nucleophile causes something known as the inversion of configuration, in the same way that an umbrella blows inside out in a storm. This is known as the Walden inversion, since the SN2 reaction is said to be stereospecific. This is a reaction where the starting reagents differ only in their configuration and are converted into stereoisomeric products, which we'll look at in more detail later in the next unit of this topic. Okay, so here's just a short video kind of showing what's happening here. Okay, so you've got your methylchlorine. Okay, then we're going to have the nucleophile attack. There's going to be the transition state, which you just see right there. The chloride leaving the product, ethanol, and the chloride ion. Okay, that's just a short animation, kind of visualizing it. So the important things to note when drawing mechanisms for SN2 reactions is the curly arrows from the nucleophile originate from its lone pair or negative charge terminating at the carbon atom, okay, which we see here. That's the first thing to note. The second point is the curly arrow representing the chlorine leaving group originates at the bond between the carbon and bromine atoms. This is shown as chloroethane or on the transition state. Okay, so we're seeing this here. This is point 2. Partial bonds, OH, carbon, chlorine, are represented by dotted lines in the transition state. Okay, that's point 3. Transition state is enclosed in square brackets as a single negative charge. Okay, that's point 4. And the formation of the product and the leaving group must be shown. Okay, so there we go. That's point 5 for the SN2 reaction mechanism. So that's for primary halogenoalkanes. So tertiary halogenoalkanes undergo nucleophilic substitution reactions involving not one, but 2 steps. The rate determining step involves the halogenoalkane, and the bond to the leaving group breaks, forming something known as a carbocation, which we looked at briefly. Okay? So due to steric hindrance, the halogen must be heterolytically removed to create a carbocation before the nucleophile can be attached. So for example, the reaction between 2-chloro-2-methylpropane and aqueous hydroxide ion leads to 2-methylpropan-2-ol and a chloride ion. The rate determining step involves only the halogen alkane, so the bond to the leaving group breaks first, forming a carbocation. Therefore, the reaction is first order. Okay, so it's dependent on only the concentration of the halogenoalkane. So it forms a stable carbocation intermediate, and it's unimolecular because the rate determining step only involves this one species. Polar protic solvents are preferred, which are able to form hydrogen bonds which stabilize the carbocation by ion-dipole interactions, like water and alcohol would be great solvents for that. Okay, and that's illustrated here in this diagram. So, it can also be, this carbocation can also be stabilized by something known as inductive effects. So the inductive effects of an organic compound have a significant effect on which nucleophile substitution mechanism occurs between a nucleophile and a halogenoalkane. The most important factor is the difference in electronegativity between atoms presented in the molecule. In the CH bond, the carbon atom has a slightly greater electronegativity than the hydrogen, creating a kind of weak dipole. Okay, so it's going to be slightly, for the hydrogens are going to be slightly negative, and it's going to be slightly positive. Okay, and it shifts the position of the bonding electrons closer to the carbon atoms. Okay, the other atoms, such as more electronegative halogens, have far greater polarizing effects on a sigma bond. Alkyl groups, which we see here in this diagram, bonded to a carbocation have a positive inductive effect, stabilizing the charged carbocation by donating electron density and reducing the positive charge on the carbon atom. In a primary carbocation, there's only one alkyl group, whereas you can see for this tertiary carbocation, you've got three alkyl groups, so it will be more stable. This is one reason why tertiary halogenoalkanes have a tendency to undergo reactions via the SN1 mechanism. So here is the SN1 reaction mechanism, and the example given is the reaction between 2-chloro, 2-methylpropane and aqueous hydroxide ions to yield 2-methylpropane-2-ol and a chloride ion. Okay, so you have to know the mechanism. The reaction has a molecularity of 1, as we've already looked at, as there is only one molecular entity involved in the elementary reaction, and it is hence termed unimolecular. The atoms present in the molecule influence the stability of the possible intermediates, as we've discussed. Okay, so the tertiary carbocation is going to be stabilized by those three alkyl groups. Okay, so what happens is that you have the chloride ion leaving, which is the slow step to form the carbocation intermediate, and then quickly the hydroxide nucleophile attacks the carbocation to yield the corresponding tertiary alcohol. Okay, and here is just a small animation illustrating that point. Okay, so here you have the compound, the tertiary alcohol, chloride being attacked. There's the leaving group, carbocation intermediate, and then the covalent bond forms between the hydroxide and the carbocation carbon, leaving the tertiary alcohol. Okay, so just like the SN2 reaction mechanism, there are of course rules for drawing. So the curly arrow representing the halogen leaving group originates at the bond between the carbon and the halogen. Okay, so that's point 1 that you need to have drawn on your mechanism. The next point is the representation of the carbocation clearly shows where the positive charge is centered on the carbon atom. Okay, so that's point 2 there. You can see it's on that carbon. The curly arrow of the nucleophile originates from its lone pair or negative charge terminating at the carbon atom. Okay, that's what that illustrates there. That's point 3. And finally, the formation of the product and the leaving group must be shown. So we've got to put a chloride ion on there, and that's the last point. Okay, show both products. So, again, factors affecting the rate of nucleophilic substitution. Okay, the presence of a good leaving group in the reactant and undergoing nucleophilic substitution increases the rate of reaction in both SN1 and SN2 mechanisms. In both cases, the rate determining step involves the heterolytic fission of a carbon-halogen bond in which there are two bonding electrons move to the more electronegative atom. The quicker this rate determining step is completed, the higher the rate of reaction, and the better leaving group will help achieve this goal. So bond strength as well as electronegativity is important in choosing a leaving group. Fluoroalkanes, okay, these guys here, are virtually inert due to the short length. It's about 138 ppm. Okay, for those particular alkanes. And the high strength of the carbon-fluorine bond. It's about 492 kilojoules per mole. Okay. As you move down the halogen group, the strength of the carbon-halogen bond decreases as the size of the halogen atom increases. Okay, so the electrons are getting further away from the nucleus. There's pull on the electrons, and the larger halogen results in longer, weaker bonds. Additionally, the stability of the halogen anion formed during the reactions is directly related to the effectiveness of as it is as a leaving group. The larger iodine atom can better dissipate the negative charge compared with the chlorine atom, and so iodine is a better leaving group than both fluorine and chlorine. Okay, so that's how we determine the effect of the leaving group. We've also got the effect of the mechanism. Okay, in general, SN1 tertiary reaction rates are faster than SN2 primary due to the stability of the formation of the carbocations, as we've just discussed. Okay, the class of halogenyl alkane has a direct effect on the rate of the formation of the carbocation, okay, and hence the overall rate of reaction, because a tertiary carbocation has a greater stability than a primary carbocation due to the inductive effects of the alkyl groups bonded to that central carbon. This is formed, of course, following the cleavage of the carbon-halogen bond, and more stable tertiary carbocations rapidly form and immediately react with the associated nucleophile. So that is essentially SN1 and SN2 nucleophilic reactions. So the next class of compounds is, next class of reactions is electrophilic addition reactions, which of course we see with the alkenes. Okay, so again the mechanism must be known. Okay, so in contrast to a nucleophile, an electrophile is an electron deficient species that will accept a pair of electrons. We've looked at these definitions earlier. It acts as a Lewis acid. Okay, so examples of electrophiles include methyl cations, CH3+, or nitronium ions, NO2+. Electrophiles either have a formal positive charge, a cation, or a partially positive charge. Okay, due essentially to the generation of the presence of a hydroelectronegative species, resulting in the polarization of bonds. So this is an example, of course, of an alkene, and they contain this electron-dense carbon-carbon double bond. Okay, and they undergo addition reactions in which the double bond breaks and two additional atoms bond with the molecule. So this, of course, creates the saturated product at the end. So the carbon-carbon double bond contains, of course, a sigma bond and a pi bond. And the sigma bond is formed by the end-to-end overlap, of course, of orbitals. We've looked at that previously. And a pi bond is formed by the sideways overlap of atomic orbitals and electron density above and below the plane of the bond. Okay? So the distinction at this point must be made between the strength of the bond and its reactivity. In terms of bond association energy, the double bond is stronger than the single bond. But the higher density of the electrons in the double bond mean that it's more susceptible to electrophilic attack, say from this bromide. Sorry, not electrophilic, the bromate, the Br+. Bromide's nucleophile. Okay, so there's the example there of ethene and HBr. Okay, so that's kind of the mechanism that you need to know. So essentially what you've got is you've got the polar HBr. The proton becomes slightly positive, the bromine becomes slightly negative. H+ is a very good electrophile. It's going to attack the electron-rich double bond, forming the carbocation intermediate on the corresponding carbon or adjacent carbon, and then the nucleophilic bromide is going to attack the carbocation, and therefore you get the associated saturated product. And you have to know this mechanism. So in terms of asymmetric alkenes, you have to have an understanding of Markovnikov's rule. Okay, the rich get richer. That's how I like to remember it. Okay, So the major products of electrophilic addition of hydrogen halides to unsymmetrical alkenes can be predicted by using this rule. The hydrogen atom will preferably bond to the carbon of the alkene that has already been bonded to the largest number of hydrogen substituents. So that's why I say the rich get richer. Okay? This comes about because of this point here in the diagram. Okay? Because the carbocation formed when the pi bond is broken has a positive charge centered on the most substituted carbon. I'll get there in the end. A tertiary carbocation has greater stability, which we looked at earlier, than a primary carbocation due to the reduction in density of the positive charge due to the inductive effects. Okay, so this guy here is going to be more stable than that guy there. Okay, because it's got two alkyl groups acting as inductive, or giving electron density to the carbocation, making it more stable. Okay, so that's why the rich get richer. So just put that there, the rich get richer. Okay, so let's look at the example of propene and HBr to illustrate the point of Markovnikov's rule. Okay, so Markovnikov's rule is going to state that the hydrogen atom will preferably bond to the carbon atom of the alkene that is already bonded to the largest number of hydrogen substituents. Okay, so if we form the carbocation intermediate, as we've done here, okay, you will see that that guy has one hydrogen attached to it, two hydrogens attached to it. Okay, and that one only has one hydrogen attached. So Markovnikov says, well, the hydrogen is going to form on the one with the most hydrogen substituents, so it's going to be this carbon here will have the hydrogen. Okay, it's Markovnikov's in action. Okay, so in terms of drawing the mechanisms for this particular reaction, the curly arrow originates from the carbon-carbon double bond to the hydrogen atom of the hydrogen bromide. Okay, that's first step there. That's where the electrons go. Okay, that's step number one. And then the curly arrow representing the bromine leaving group originates from the bond between the hydrogen and the bromine atom. That's point 2. The curly arrow goes from the lone pair or the negative charge of the bromide to the carbocation. Okay, that's point 3. And finally, the structural formula of the product is finally shown. That's point 4. So the final kind of reaction we're looking at today is the electrophilic substitution reactions, in this particular case of benzene. Okay. So let's now look at the nitration of benzene. You have to know this mechanism. Okay. So the first step requires the nitronium ion electrophile to be formed. Okay, from the nitric acid. Pure nitric acid contains only a small concentration of this nucleophile, but a nitrating mixture of sulfuric acid and nitric acid at 50 degrees, put the conditions there, 50 degrees C, generates a higher concentration of nitronium ions, allowing the reaction to proceed at an acceptable rate. Sulfuric acid protonates nitric acid, which we see here. Subsequently releases a water molecule to generate the associated nucleophile that we want. Okay, the nitronium ion. The nitronium ion is a strong electrophile. As the electrophile approaches the delocalized pi electrons, okay, which is what we're seeing here, okay, of the benzene ring, the nitronium ion is attracted to the ring, okay, positive and negative attract. 2 electrons from the ring are donated to form the new CN bond. Okay. Additionally, a pi electron from the NO double bond of the nitronium ion moves to the oxygen atom. Okay, that's what we're seeing in this step here. This is actually the rate determining step. Okay, this one here, the rate determining step. The addition of the nitronium ion to the carbon-carbon bubble bond eliminates the aromaticity of the arene. Okay, and what do we mean by that? Basically the stability of the resonance form. Then water acts as a base, deprotonating the carbocation intermediate and restoring the aromaticity of the system to get the final product, the nitrobenzene plus a proton. Okay, and this is a yellow oil that can then be extracted from the reaction mechanism. Okay, so in terms of the mechanism, let's just go through it in a little bit more detail. The curly arrow has to originate from the delocalized electrons in the benzene and terminate at the nitro. Okay, so that is the first, what am I doing? That's the first thing you need to draw. The structural representation of the carbocation shows a partial broken line circle and a positively charged ring. Okay, so that's step 2, which you need to be able to draw. The curly arrow represented by the hydrogen ion leaving originates at the bond between the carbon and the hydrogen atoms and terminates at the benzene ring cation. Okay. So that's actually not been drawn in there. I'm just going to do it. So it's going to go into there. Okay, so that's point 3. And finally, the structural formula of the organic product nitrobenzene is shown, plus the released proton. There it is, step 4. So then we have the reduction reactions of alcohols and again our friend nitrobenzene. So in terms of the reduction of carbonyl compounds, we've already looked at this in a little bit of detail in the last lesson when we looked at oxidation of ethanol up to ethanoic acid. Now we're going the other way. We're reducing ethanoic acid down to ethanol. Okay, so carboxylic acids are reduced to aldehydes and eventually to primary alcohols when you reduce ethanoic acid or a primary acid. Okay, when ketones are reduced, you get down to secondary alcohols and you can't do anything with tertiary. Okay, so the two commonly used reducing agents are lithyl or lithium aluminium hydride and sodium borohydride, NaBH4. Okay, so there we go, lithyl there, as we used to call it in the lab, and sodium borohydride. Okay. Lithium aluminium hydride is regarded as a nucleophile reducing agent that will reduce the polar carbonyl or CO double bond represented in carboxylic acids, aldehydes and ketones, and lithyl is known as a stronger reducing agent than sodium borohydride because sodium borohydride will only reduce aldehydes to ketones and to alcohols. So the reduction equation is often represented by simply putting a H above, okay, like that, okay, and this represents essentially the reducing agent, be it sodium borohydride or lithium aluminium hydride. Therefore, you can define the simpler equations as such. Okay. So in terms of the reduction of nitrobenzene, you don't use lithyl, you use something else. Okay, so this is actually was part of my PhD. So nitrobenzene using tin and concentrated hydrochloric acid is the example that has been given in your textbook that you have to know the mechanism for. So essentially the nitro is being reduced to a phenylammonium intermediate, which we see here, okay, and then the phenylammonium intermediate is reacted with dilute base, okay, and what happens is you extract the phenylamine product, usually fractionally distillate off, plus water, and those are the two products. Okay, so that's pretty much all you need to know for the mechanisms associated with organic chemistry. The next lesson we're going to look more around the stereochemistry that we briefly touched on in this lesson in a little bit more detail.